Sora, that's the symbol you're looking for. If it disappears, tell me right away. It is September 15th. We're looking at infinite limits. What we've done over the last couple days is we've talked about how to deal with limits where we're continuous, really easy, you just plug in. Where there's a hole, plugging in gives 0 over 0, we factor and cancel or simplify some other way, we can deal with that limit. The jumps where the limit doesn't exist, but we can look at our one-sided limits and kind of understand jumps that way. Today we deal with the language for dealing with vertical asymptotes and how to get vertical asymptotes out of formulas and all of that. For starters, though, I'd like to take a look at the function f of x equals 1 over x. And this is a graph that you first saw in Algebra 2. It's one of those things with some asymptotes. Looks like that. Looks like that. I guess I should probably stick some arrows on the ends. And I want to look at three things. I want to look at the limit as x approaches 0 from the left of 1 over x. I want to look at the limit as x approaches 0 from the right of 1 over x. And I want to look at the limit as x approaches 0 in general of 1 over x. Okay, none of these actually exist. We talked about this on the first day. We could say all of these don't exist. However, there's some better language we need to see for describing some of these limits, even though they don't exist. As I approach 0 from the left of 1 over x, well, this thing is going down all the way over there, not approaching a number, but approaching the idea of what? We're going to say this limit, even though it doesn't exist, it can be better described as negative infinity. Limit as x approaches 0 from the right of 1 over x. What would you call that one? As we approach 0 from the right side, infinity. It still doesn't exist. This is just a better way, though, to describe it. And from here on out, if you can say negative infinity or infinity, I want you to say that. So what's the overall limit? This one
does not exist.
This one still won't exist, not because of the vertical asymptote so much, but because you're going in two different directions. If they were both going up, we could say that was infinity or something like that. I would like to try a few of these from a worksheet. Let me get this out to you. Yep. Two. Only two. Need one. Thank you. Yep. So, I'd like you to take a moment, look at that worksheet titled Section 1.5 Graphical and Numerical Limits. I know we didn't just talk about this numerically, but I bet you can figure that out. See what you can do, and when you're done, check in with someone near you, and we'll talk in a few moments. And again, from here on out, we're no longer going to say does not exist if we can better describe it by infinity or negative infinity. again, please do, when you're done, check in with someone near you. Yes, tell your parents to come to parent nights. We haven't had one of these in 2 years.
Okay.
Tell them to come to nights. Open house. They go to all your classes and stuff. 7 o'clock. They're all going to be here. Yes. 6:30. Okay, let's go through this stuff and see what's going on. Yeah, I am realizing that there hasn't been one of these since you people were freshmen. And that was a long time ago. Tell your parents, come tonight, 7 o'clock. Let's look at these. Bennett, what did you say for letter A? Limit as x approaches -2 from the left. Infinity, good. And Mahalis, what about B? Also infinity. You know, I can say equals infinity, that's okay. Akash, what did you say about C? Because A and B agreed, we'll say this is infinity. We're not going to say does not exist for that one, because it does agree from both sides. Sora, how about D? That has nothing to do with vertical asymptotes, but that still works. Ehit, what about E? Infinity, yep. And April, what about F? Negative infinity. Therefore, Shri, what do you have for G? Yeah, because those two things didn't agree. That one doesn't exist. Anything here? Number 2. Melissa, what did you say about A? Yeah, I think so. And Tyler, how about B? Infinity, I like it. And Alexandra, what about C? Because A and B don't agree. Andrew, how about D? 1. Sophie, what about E? 3 sounds good. Ella, what about F? 1. Olivia, what about G? Does not exist. And Sora, what about H? 3, because that's where the filled in dot is. Anything? You can probably assume when we get to a test, it's going to start with a really big, as complicated as I can make it graph with some holes and jumps and asymptotes, and I'll just make you do all these little pieces. Not super hard, just lots of things I'm going to try to throw into one problem. Let's try to figure out the limits from the table. Limit as x approaches 1 from the left. Volunteer. Mahalis. Looks like -10, -100, it's going down very, very, very quickly. That's our sign that it's an asymptote, and since it's going down, in this case, negative infinity. Oh, you mean you actually want to see things? Don't just whisper that next time. Actually, just say it, because I'm not gonna notice those things, and then the people at home won't have a clue what's going on. So yes, tell me to move the paper up. The other one, as we approach 1 from the right. Infinity. So Andrew, what about the overall limit?
Does not exist.
That does not contradict what I told you before. It still doesn't exist. But the other ones now we can just describe a little bit better. Do you see how to do this from graphs, from tables? The rest of today will be about how to do this analytically. So, analytical infinite limits. And please, again, if the paper is not on the screen, tell me to move it up. I'm going to have no clue. I'm not looking behind me. And Sora, again, if the recording button disappears, tell me. Analytical infinite limits. Just like with holes, that gave us 0 over 0, although maybe that's not 100% technically correct, because we already saw some, like, we saw a 0 over 0 that was really a jump. But if it was 0 over 0 and then simplifying gave us a good number, that's our sign. There's a hole. There's a sign that tells us we're going to have a vertical asymptote, and we might get infinity or negative infinity, or maybe even does not exist. These infinite limits will occur when plugging in gives us a number that is not 0 over 0. These occur when plugging in gives a number, and by the way, when I say a number, I mean like a non-zero number. Some non-zero number over 0. That's our sign that if you plug in and get, that's why I want to start every problem by plugging in 0 over 0, you know you've got your tricks for that. 5 over 0, that's going to give us one of these infinity cases. To evaluate. First of all, just like our jumps, you cannot handle an overall limit where you have a number over 0. So if it is an overall limit, you're going to start by splitting it into a limit from the left and a limit from the right. To evaluate, split into a left and a right limit if it's not already a one-sided limit. Can't deal with an overall limit. I feel like you just saw this on the graphs. One side was infinity, the other side negative infinity. The overall thing didn't exist. We got to deal with the two things separately and then reach a conclusion about an overall limit if that's what I happen to have. To evaluate, though, we are going to evaluate this numerically. And what I mean by that is just plug in our number to the top. Plug in the number to the top. And at the same time, we're going to plug in something very close to the bottom. And I'll show you exactly what that means in a moment. Plug in something very close to the bottom. So for a first example, we're going to look at the limit as x approaches 1 from the left of x squared minus 3x over x minus 1. Forget about everything I just taught you. What do we do first no matter what? Plug in. Should I say this limit equals what I'm going to get when I plug in? That's what I just talked about with those quizzes. No, this is just going to be like sort of work on the side. You don't even have to show the plugging in work. But what do you get up top when you plug in? -2. What do you got on the bottom? 0, which means it's in the form to be one of our infinite limits. If it was 0 over 0, you know you'd go to your simplifying tricks. Not the case here. And this is a really big deal because what I'm about to show you, you can only use in this case. If you try using this method when it's 0 over 0, it's not going to get you anything reasonable. So what I'm going to do now is I'm going to plug in I'm going to say this equals 1 squared minus 3 times 1 up top. I'm going to plug in exactly to the top. And by the way, I'm plugging in, which means I'm no longer writing my limit symbol. I'm not going to plug 1 into the bottom, though, because I know that's going to give me 0. Instead, I'm going to plug in something very, very close to 1. Something a little to the left of 1 that's very, very close. What's a really close number to 1 that's a little to the left?
0.9.
Yeah, get closer than 0.9.
0.99.
0.99, get closer.
0.999.
Yeah, let me write a whole bunch of those, like 0.9999999 minus 1. The top is just negative 2. You knew that was negative 2. The bottom, though, is a really small number, right? 0.99999 minus 1. What sort of a small number, though? Small positive or a small negative?
Small negative.
Negative. I'm going to write small negative. Just for fun, for this first one, take out your calculator. You probably already know this, but just to confirm, forget about this particular problem. If I gave you, like, 5 divided by a really small number, 0.000000001, what sort of answer would you get? 5 over a really small number.
Really large one.
A really big number, right? If the bottom is really small, wouldn't the answer become really big? So like, infinity big. The only thing I have to decide, though, is it infinity or is it negative infinity? Anyone have an idea how I would figure that out? Sophie?
Well, if the top is negative and the bottom is negative, then you're positive.
All of our sign rules for division still work. A negative over a negative is a positive. So what sort of infinity are we going to get? We're going to get positive infinity. And this is what your work's going to look like for these. Very different than work we've done for other sorts of problems. And it is so important that this work is only shown when it's a number over 0. It will not give you anything valid in the other cases. Let's do another one. You know what? Let me do the exact same problem, but let me do the limit as x approaches 1 from the right of x squared minus 3x over x minus 1. And I think by now you already know what plugging in will give us. Right, it's still the same as the last problem, still negative 2 over 0. So I'm going to say this equals. Now, up top, you are not plugging in something close to 1. You actually are plugging in 1 because you can handle plugging that into the top. We're going to say 1 squared minus 3 times 1. I don't want to see 0.999s or something on the top. What should you plug into the bottom, though? Ins. Tyler. 1.111, get closer. Sora. And a 1 at the end. 1.111 is a little too far away. I want really, really, really close to 1. 1.00001 or something like that. That's negative 2 over a really small number. Small what? Positive. You know if the bottom is small, but the top is not. By the way, the reason we're not plugging in something close, well, no. The reason this doesn't work with other problems is you can't say like a small number over a small number because that could be 1, that could be 0, that could be infinite. That's not useful here. That's why the top has got to be a reasonable number, not like a 0 number. Negative 2 over a small positive, what sort of infinity? Positive or negative? Just say it. Negative, sure. Negative over a positive will give you negative infinity. I might as well do one more like this since we're on this. If I want to do the limit as x approaches 1 of x squared minus 3x over x minus 1, I think I can just do it right away. I know the answer. Bennett? Why does it not exist? We just did the 2 one-sided limits. They didn't agree. Therefore, this thing does not exist. And if I didn't give you the previous 2 problems, you would have to create those previous 2 problems, do your one-sided limits. Sometimes we're good, sometimes not so much. Anything so far? Next. I would like to take a look at, actually no, you're going to do this one. You're going to go do the limit as x approaches negative 3 from the right of x plus 2 over x plus 3. Take a moment and deal with this, and that's all I'm going to say. Did you first plug in just to be safe and to do your check? Was it, Melissa, what did you get when you just plugged in? Yeah, which means, yeah, it's in our form to do our infinite limit stuff. What am I about to plug in? Negative 3.000001 or negative 2.99999? Yeah, did you say that? And if you didn't, think about how the number line works. 0, negative 1, negative 2, negative 3. If we're a little to the right of negative 3, yeah, that's negative 2.99999. This is negative 1 over a small positive. So I think you're going to say negative infinity. Let's do this. Limit as x approaches 1 of 2 minus x over x minus 1 squared. Limit as x approaches 1 of 2 minus x over x minus 1 in parentheses squared. What do you do first, of course? Plug in. And 1 over 0. Okay. What am I going to need to do? Olivia, you can't deal with this as written. If this is on a quiz and you just give me an answer, that's not going to cut it. I've got to see you creating 2 separate limits. We're going to say split into the limit as x approaches 1 from the left of 2 minus x over x minus 1 squared, and the limit as x approaches 1 from the right of 2 minus x over x minus 1 squared. I think maybe we'll do one of these together, you'll do the other one, and then you'll try to reach a conclusion. Only because the square, I just want to make sure we can handle the square. You're going to plug in 1 to the top, 2 minus 1. You're going to plug in something a little to the left of 1, so 0.9999 minus 1 squared. What is 0.99999 minus 1? Small negative, small negative. We're going to say small negative, which I'm going to square. What happens if you take a small number and square it? Yeah, keep talking, Sophie. It gets even smaller, and Sora, what were you motioning? And becomes positive, right? A negative times negative is a positive. So this is 1 over an even smaller, don't really care about that, but still a small positive. Therefore, the answer to this limit is positive infinity. I would like you to go through the same sort of work for the limit as x approaches 1 from the right, and when you're done, let's try to reach a conclusion about the overall limit. Infinity or negative infinity or does not exist. So 2 minus 1 over 1.0001 minus 1 squared. 1 over a small positive, which you're squaring is still 1 over a small positive. So I think that one's infinity too. So what I was really looking for, that original problem, limit as x approaches 1 of 2 minus x over x minus 1 squared. Yeah, that's infinity. But this is the work I'm going to need to see. Anything from you people? Next one. I would like you to go do the limit as x approaches 4 from the right of x squared minus x minus 12 over x squared minus 8x plus 16. How are you starting it? Do it. Let's just make sure it's a number over 0. Yes? No? Bennett? What is it? You getting 0 over 0? Okay, can you take out your flowcharts for just a moment? I want to mention one thing there. Maybe I have possibly. In those flowcharts, it says the first thing you do is look to see if we're doing the limit as we approach a number or infinity. We're not dealing with the infinities until later next week, so we're still following the number branch. Is it absolute value or piecewise? No, it's not. We're plugging in. We get 0 over 0. I guess I shouldn't have told you that 0 over 0 necessarily means a whole. 0 over 0 means we're not ready to come up with an answer. We need to do what? Simplify. We're going to simplify, and then we're going to plug back in. And maybe it's a number over a number, and maybe I'm done. Or maybe it's a number over 0, and then I might have one of these infinity things. But you can't tell anything right now from 0 over 0. So take a moment, simplify. I feel like the method of simplifying should just sort of jump right out at you in this problem. I hope you're thinking factor and cancel. Factor and cancel, you should be able to turn this into the limit as x approaches 4 from the right of x plus 3 over x minus 4. What happens now when you plug in? A number over 0. This is going to be one of our infinity things. So 0 over 0 technically means just simplify. If then when you plug in you get a number over number, that's your whole and things are good. But if it's 0 over 0, you simplify and now becomes a number over 0, well, that actually means it's a vertical asymptote. Finish this one off now. Go do your plug into the top, plug in something close to the bottom. Plus 3 over 4.00001 minus 4. 7 over a small positive, which should give me infinity. I have one more of these that I want to look at. Then we're going to spend just a moment talking about how to get equations of vertical asymptotes, which will really not be much of anything. And that should do it for today. And then by the time we're done today, we should be done with everything for our next quiz. Not tomorrow, but first time I see you next week. So I think that's Tuesday of next week, I think. Whatever your calendar, we're totally on track with what's on your calendar. Last of these limit problems. Let's do the limit as x approaches pi from the left of the cotangent of x. You know how I said trig's never really going away? Yeah, trig's never really going away. And I am not the biggest fan in the world of cotangents. What makes it easier to do? Cosine over, let's do a cosine over sine. Let's say this is the limit as x approaches pi from the left of the cosine of x. By the way, make sure when you're writing this out there's an x inside there, just like there's got to be something inside the limit. There's got to be something inside your sine or cosine function itself. What's the cosine of pi? -1. What's the sine of pi? This is in our form to get one of our infinity things. And actually, from the summer work test, you remember that there were asymptotes on the graph of this thing. But now let's see how to do this for real, like from the formula. I'm going to plug in pi to the top. And I'm going to plug, oh, you know what? This is going to be ugly. How about I just go straight to what happens when I've plugged in? I know the cosine of pi is -1. The sine, though, of something a little less than pi. Try it. I want to try to figure out what's the sine of something a little less than pi. Okay, but let's just jump to the end and what sort of answer are we getting? Like a small positive, a small negative, 5, 22? Yeah. Why?
Because if it's a little less than pi, it just happens to be the graph in the second quadrant and sine is positive.
Yeah, we can think about, I think the way to do this is, let's think about our unit circle on these things. Pi is the angle that goes from here all the way over to there. If you're a little less than pi, you didn't quite make it to pi, which means you're over there. The sine is the height. What's the height of that thing? Well, it's a small positive number. So this is going to be -1 over a small positive. I think if we can visualize what these angles are looking like and go a little bit before, or in other cases maybe a little after, that's where we're going to get our idea. The geometric idea of the unit circle is kind of a big deal for this. So what is this thing? -infinity. If you pull out your summer work test, which I'm not going to tell you to do right now, but if you pull it out and look at the matching one in the back with the cotangent graph, and you go to pi but go a little before pi, you're going to see that vertical asymptote going down rather than going up. I feel like there's one of these trig things in the homework. Use similar logic from this. Last thing for today. We now have the language for describing vertical asymptotes. Let's see how to find these things, and that'll do it for today. Vertical asymptotes. Here's a vertical asymptote. I got one of those. Maybe I've got one of those. Maybe they're going in the same direction, or whatever. We need to give an actual, mathematically sound definition of a vertical asymptote. You know from Algebra 2, you go way up, you go way down. That's not super technical. We need to give a technical definition of this. Well, don't I have a vertical asymptote somewhere if the limit at that place is infinity or -infinity or something like that? If. And you know what? Since this limit doesn't exist, why don't I talk about either this one-sided limit or that one? If any of those things are happening, then I'll have a vertical asymptote. If the limit as x approaches c from the right of f of x, or the limit as x approaches c from the left of f of x, if either of those limits are infinity or -infinity. I guess I could have just said plus or minus infinity. If we do a one-sided limit at a particular x value and get infinity or -infinity, then f of x has a vertical asymptote at x equals c. This is my actual definition of a vertical asymptote. If at that x value, if I do my limit from the left or my limit from the right, I get infinity or -infinity, I have a vertical asymptote there. to find vertical asymptotes. Well, what gives me the infinity or negative infinity thing? I know that happens when I have some non-zero number over 0. So really, all I need to do, I don't need to go to all that limit stuff. All I need to do is look for places where the denominator is 0, however, the numerator is not. I want to find where the denominator equals 0, but the numerator does not. Because that means I'm in my 2 over 0 or negative 3 over 0 form, which is what gives me the infinities and negative infinities and all that. We're going to take a look at 3 problems. We're going to find vertical asymptotes, and that should do it. So, first example, we are going to find the vertical asymptotes of letter A. Let's deal with the function f of x equals x squared plus 1 over x squared minus 1. X squared plus 1 over x squared minus 1. And, okay, maybe this one's not super complicated, but in general, what might make this easier to deal with if we did? It starts with an f. What should I do? I should do some factoring. What happens when you factor x squared plus 1? Are you telling me you can't do it? Ah, okay. So, for those of you at home who didn't hear, Olivia just said imaginary numbers. I don't think I've mentioned that to you guys yet. In this course, we will not deal with any imaginary numbers. That's going to be like a college post-calculus thing if you get to stuff like that. So, can we factor the top? No, we're going to leave it. That's actually pretty nice that we're not going to have to deal with imaginary numbers in here. Bottom, though, you can totally factor. Bottom is x plus 1, x minus 1. What would make the denominator equal 0? Well, negative 1 and positive 1. Neither of those make the top 0. When you give me a vertical asymptote, though, what do you have to actually say in the answer, thinking back to like Algebra 2 pre-calc? It's x equals their lines. I want the equation of a vertical line. So you're going to say x equals negative 1, x equals positive 1. Those are the equations of the vertical asymptotes. I needed to look at the top just to make sure the top wouldn't be 0. But as long as it's not, I've got my vertical asymptotes coming from the bottom. Deal with f of x equals x squared plus 10x plus 21 over x squared minus 9, please. Find the equations of the vertical asymptotes. And I certainly hope your first thought was to factor this thing. X plus 7, x plus 3, x minus 3, x plus 3, vertical asymptotes at x equals 3. X equals negative 3. Good. Why are you shaking your head? What's wrong?
Because there's a hole at x equals negative 3.
Negative 3 is going to make the top and the bottom equal 0. That doesn't count. We'll get into more specifics next time, but Andrew is totally right. That will be a hole. X equals positive 3 is the only vertical asymptote. Look for where the denominator is 0, but if the numerator is also 0 because it has that factor, it doesn't count as a vertical asymptote. One more. I think we should do a trig one. F of x equals the secant of x. So we look for where the denominator is 0. Oh, wait, I don't see a denominator. Does anyone see a denominator? That's how we get our denominator of it. And that's also why we need to go into sines and cosines, so we see a denominator. Vertical asymptotes at x equals. Okay, so all we have to do is figure out what would make the cosine 0. Pi over 2. And what? Pi over 2, 3 pi over 2. However, you know what? I didn't actually tell you. We're just sticking to one time around the unit circle. We can keep going. 5 pi over 2. 7 pi over 2. Negative pi over 2. Negative 3 pi over 2. There are really infinitely many of these things. I think last year you saw a way that we can write this if we're not just sticking with 0 to 2 pi. We can say this is x equals pi over 2. How far away is 3 pi over 2 from pi over 2? Pi. How far away is 5 pi over 2 from pi over 2? From pi over 2. 2 pi. How far away is 7 pi over 2 from pi over 2? How far is negative pi over 2 away from pi over 2? Negative pi. Negative 2. So really, plus like any multiple of pi will get us there. Anyone remember how to say that? Yeah. Well, almost. K. Can K be absolutely any number? 1 pi, 2 pi, 3 pi, negative 1 pi, negative 2 pi, negative 2.5 pi, negative root 6 pi. All those are good? Okay. Where K is an integer is the correct answer. Or if you want to be super fancy and remember some symbols from Algebra 2, we could also say K is, anyone remember the fancy symbol for integer? It's the not obvious one at all. I know your Algebra 2 teacher taught you that one. And yours did too.
Is it I with like double bars?
Nope. Q is for rational because of quotients. Fancy Z. This is the one that's not super obvious. This comes from the German Zahlen, which means number. They came up with the integers first, so they got that there. If you don't remember that, I don't care. K is an integer is totally fine. But technically, it shouldn't be just pi over 2. And neither should it be pi over 2 plus pi k. What sort of multiples of pi? Integer multiples of pi. That's what I've got. Oh, it never actually shut off during the period, which means I think I recorded this whole thing. I'm going to not push the power button on.